All right. I'll let you guys finish up your green cards. See a couple people still writing. No.
I was like, whoa, I don't think you can do that.
All right. So what do you think? E3 was a great assignment to have on a virtual day, right?
Yeah.
Yeah. This was, I mean, this is the picture. I was sitting 30 miles away from you, trying to explain this. The whole thing with the integrals is we're trying to find an area under a curve, correct? That part where we know about. We do that by making rectangles, or in some cases trapezoids, but mostly we think about rectangles because they are the simplest shape. You just multiply the length times the width. When we have control, so if you guys worked on E2, sometimes you have a table of values and you don't have control over this, but when we have control, we make our intervals even. So all of our rectangles have the same width, okay? If we are doing it in a finite version for an estimate, like we were doing on Friday, we'll have an interval or pick an interval. So on the left example, the interval was from 1 to 4. We'll decide how many rectangles we want to draw. In our case on the left, we were told to do 6 of them, which meant that each rectangle had an interval of 1/2, okay? That interval length is what we call delta x. Anytime we use a delta x, that means we're talking about in finite terms. And by finite, I mean we've got a countable number of rectangles. When we define the integral in a minute, we're going to take the number of rectangles, we're going to take the limit as the number of rectangles goes to infinity. So we are going to make smaller and smaller rectangles, which will give us better and better estimates. And when we take that limit to infinity to see where those estimates are headed, we will get the exact area under the curve rather than an estimate, okay? This is way more complicated than what we did with derivatives, because a derivative was just a slope of a line. So we took the limit of a slope of a line as the 2 points got closer and closer together. Here we had to introduce summation notation because we are not taking the limit of one thing. We are taking a bunch of little areas and adding them up. So that's why we needed summation notation. We looked at it in kind of 2 cases. We looked at it with some specific numbers, and we looked at it in a little bit of general terms. But what we had written here as our answer for letter B were basically just, they kind of came from the same place. On letter B, I said I wanted 6 rectangles, and I wanted them to span between 1 and 4. In letter B on the right, I had n rectangles instead of 6, and they spanned from whatever x equals a was to x equals b. So we're going to see this in a minute, that this is kind of a general thing we need to know, this definition for delta x, and it does match what you wrote on your card earlier. Okay. So the rest of this, the goal here, and I did write myself a note after the lecture to kind of incorporate this somewhere in. Our goal is to write a mathematical expression in kind of a compact form that just kind of walks you through the process of finding the area of each of those rectangles and then adding them up. So what we have at the bottom here represents taking 6 rectangles, rectangle 1 through 6, calculating their area. Each one of those areas had one dimension, or sorry, each one of those rectangles had a dimension that was equal to 1/2, right? Because each one, the bottom of it was 1/2 of a unit wide. And then each height was based on our function, which was the square root of x, but we had to take that square root of x at a certain spot. So this just represents base times height, and we're doing it 6 times, and summation means added up. So that's what this is. This is a compact set of directions that would tell you exactly what to do to find the area of those 6 rectangles, and then it tells you to add them up, okay? Does that make sense to some degree? Maya is shaking her head, but she has this look on her face that says stats. Why didn't I take stats? It's okay. All righty. The situation would be a little bit different whether we were doing a left sum or a right sum. There's a handful of little notation things I have to fix on this one. I think I just want, let me see, I was looking at it this morning. Yeah, both of these should just say f of xk. So you can cross that -1 off there. Okay. You can do this with a left sum, a right sum, a midpoint sum, or a trapezoidal sum. We're going to cut that in half and only look at right sums and left sums, okay? The major difference is where the rectangles get their height from. Up here, I have it in the order that we did it in. We did a right sum last Friday, and this is what a left sum looks like. So when you do a right sum, the first x value that you plug in to find the height of the rectangle is x1, which comes from taking your starting value a and adding 1 interval to it, 1 delta x, okay? So x1, the first height, is a plus 1 times delta x. Delta x is defined as how wide the bases of these rectangles are. So we take where a was and we add 1 base to it, and that tells us how high our rectangle needs to be. Do you guys agree with that? Does that make sense? The second rectangle happens at x2, so that's a plus 2 delta x. Because basically what we've done is we've gone over 2 amounts, and those amounts are called delta x. Okay. So this corresponds to the height of rectangle 1. This corresponds to the height of rectangle 2. Rectangle 3, which not shown, would be a plus 3 delta x. Rectangle, some random number, I plus 1, just the way that this was labeled, this would be a plus I plus 1 times delta x. Okay. Now, when we do a left sum, basically what happens is we start on the other side. So our a1 actually has a height of a plus 0 times delta x, or just a, right? So that's the major difference between a left and a right sum. Our a1 starts here, which is a plus 0 delta x. And then our a2 has a height of a plus 1 times delta x, because we're starting on the left instead of the right. So these numbers that I'm writing, this is the height of a1, this is the height of a2, this is the height of a1, this is the height of a2. So in a left sum, the number, the coefficient in front of the delta x doesn't match which rectangle you're on. In the right sum, the coefficient in front of the delta x does match which rectangle you're on. Okay. Yeah. What actually makes it nice, though, is the fact that we can kind of solve all of this with summation notation. I have this in terms of right and left on the board, but my equation down at the bottom is flipped. So I have left and right, and I have that, I don't know if it's the best idea in the world, but so that I would actually literally have the left sum on the left and the right sum on the right. So what's going on here is a little bit of a flip-flop. I know why I did it. I don't know if it was the best idea in the world. But all you have to do, the only difference between a left sum and right sum is your indexing. In the end, we're just starting, where are we starting with? Are we starting with k equals 1 or are we starting with k equals 0? So it really is just an indexing situation. The first rectangle starts with 0, delta x is added to it. So I start at k equals 0, and I stop when I hit at n minus 1. I never actually have to go the full n. There's never a rectangle with this final height. Okay. Alternatively, on a right sum, there's never a rectangle with the initial height. So A never got used. The first rectangle is A plus 1 interval. So I start with k equals 1 and go to n. The final, that final n represents the last line here. Okay, a lot of conceptual stuff in that. So now let's talk about what we have to do in these problems. This first paragraph is something that I kind of already talked about. If we take the limit as those number of subintervals goes to infinity, we make those rectangles thinner and thinner and thinner and thinner, then we get better and better estimates for the area under the curve. Taking that limit as it goes to infinity ends up being the area under the curve. So we have this definition of our integral. This is the limit definition of the integral. We write an integral, which we're saying, take the area under f of x from a to b. That's the limit as our summation goes to infinity of exactly what we were talking about on the previous slide, f of xk delta x. These indexes could match a left sum or a right sum, and they're both correct. So I could have just as easily wrote k equals 1 to n minus 1, or I could leave it as a right sum, which is k equals 1 to n. And I believe on your card, I put both of those there. So this represents the left sum, this represents the right sum, and those two limits are equal. The notation is similar. The limit of the summation is what the integral represents, right? So integral from a to b is the limit of the summation. A and b are hidden inside here. That's what we're going to see in the next set of questions. So a and b don't actually show up in this part of it. They show up over here in a couple different ways. But then f of x dx, in summation terms, it's f of xk, which is defined as something. We'll see that in a minute. That's just going to be our a plus delta xk. That's what we were doing on Friday. And the dx comes from the delta x. Okay, so delta x is a finite amount, but dx, we've squeezed that down to basically nothing. We call that an infinitesimal. That kind of comes in. It's kind of one of the things when you're first learning calculus that there's a lot of theory behind it, but it's really in the weeds. So it's just the delta x has turned into the dx. So these do represent the same thing. Integral is just shorthand notation for this limit. I also want to include the other thing that I'm missing here, which is what delta x is. Delta x is b minus a over n. And in the end, that summation represents what we developed on Friday. Make the rectangles, calculate their areas, add them up. All right. Okay, so let's see how this all works. Write the definite integral as the limit of a right Riemann sum as n approaches infinity. A right Riemann sum means you go from k equals 1 to n. If this were a left Riemann sum, I'd write k equals 0 to n minus 1. That's the only difference. Everything else stays the same. We need to identify all of this stuff from the top before we can actually do this. So I need to identify B and A. That way I'll actually have my delta X. n stays as n because that's what we're taking to infinity. So n is not something we need to figure out. N is part of the limit, so that stays as n. After we get our b and our a and our delta x, we will write out our xk. This basically is going to be where you're figuring out each individual height of your rectangle. That's what xk means. So the first xk represents the height of the first rectangle. The next xk represents the height of the second rectangle. So this is just a general formula to find the height of any rectangle along the way. So b and a are the limits. So this first part isn't super hard. If I want to say what delta x is, I just take my limits, 0 and 4, and I subtract them, and I put them over n. Delta x is 4 over n. When I go to write my answer, I'm going to replace that delta x with 4 over n. Okay. Next, we've got to figure out x sub k. X sub k is our starting value plus however many intervals deep we are into our set of rectangles. So that's going to be a plus delta xk. I wrote a, but in our case, a is 0. Delta xk is just going to be kind of a repeat, 4 over n times k. So once you have delta x, you just kind of have to piece together x sub k. I can clean that up a little bit. I don't need to write 0 plus, so I'll just write 4k over n. And the last thing that I need is now I need to take f of x sub k. So get one last color here. Now we want to know what f of x sub k is. But f is the function that we're integrating. So I'm going to take 1/2 x squared plus 1 and plug in, instead of x, my xk. Okay? So in the integral, we have f of x, but in the summation, we need f of xk. So I'm going to take, I won't generally write this first part out. I'm just going to rewrite x squared with xk in it. Right? If f of x is the thing that I have underlined, then f of xk replaces the x with xk. But what we really have here is 1/2 4 over nk, 4k over n, sorry, squared plus 1. So putting it all together and color coding it, I'm going to make one more adjustment to my color coding up here. I'm going to make that blue. I'm going to make that blue. I'm going to make that blue. So we did the f of xk, and xk was 4k over n. That integral is equal to the limit as k equals 1. No, sorry. As n goes to infinity. Sorry, I jumped ahead of myself. The limit as n goes to infinity of the summation that starts with k equals 1 and goes to n of f of xk. So that's going to be my 1/2, my 4k over n, but squared, plus 1. And that function needs to get multiplied by delta x. So in order to multiply that function by delta x, I better put that in parentheses. Otherwise, I'd only be multiplying the 1 by the delta x. And from there, I just need my delta x, which is 4 over n. Yes, sir.
You just took the integral all over.
What's that?
You just took the integral.
Something.
Can't be that guy.
It's enough complicated. I'd have to cube 4 and divide it by 2 and then add 4.
Fill up the function.
Yeah, the function that's written there, it's 4 cubed over 2. Well, 4 cubed divided by 6. Whatever 4 cubed divided by 6 is plus 4. That's the answer.
Wait, so it will be
All right.
x cubed over 6.
Yeah. Evaluated, but at 4 and then subtract it evaluated by 0. So we'll get there. That's the next lesson, Jack. Okay. That's E4. Yep. All right. Okay, so that's one direction. We're going to go in both directions with this. I'm going to give you the integral, and then you're going to have to piece together the delta x, the xk, and then the f of xk, and then just write it all together like that. We'll do 2 more examples. Maybe I'll do one and have you guys try one. Yeah. All right. Okay. I'll leave the color coding up at the top, so we'll just follow along. Difference here is we've got a left Riemann sum, so we're going to go ahead and write that, in this case, as the summation from k equals 0 to n minus 1. That's going to be the only change that we make. Both limits will be the same regardless of which one we do. Let's take a look at what we have here. We're taking the integral from -2 to 0. So the first thing we need to figure out is our delta x. That's easy. That is just b minus a, so 0 minus -2 over n, which is just 2 over n. Next, we need our x sub k, which is a plus delta x times k. What's our a value? -2. So that's going to be -2 plus delta x, which we already have. That's 2 over n times k. There's nothing I could do to clean that up other than make it 2k in the numerator, right? So I'll do that in line with the next part. And now in green, I need my f of x sub k, which is really just taking x plus 3 squared and replacing the x with -2 plus 2 over nk. So that is going to be x plus 3. So -2 plus, I want to do that in green. Or in blue, I mean, not green. So there's my xk, -2 plus 2 over nk plus 3. And then square it. Now, don't go too crazy with algebra unless you need to simplify it for one reason or the other. That would be matching. That's pretty much it. I will simplify it here, but you can leave that as is. I've got 3 things being added, and 2 of them are numbers. I'm good to collect like terms, right? Okay. So when I write it, I'm going to not write the -2 and the plus 3. I'm just going to combine those into a positive 1. So my integral here is, or sorry, my limit is, the limit as n goes to infinity. Because it's a left sum, I'm going to index starting at 0, and I'm not going to hit the last one, because that's what happens in a left sum. And it's just f of xk delta x, right? F of x dx is f of xk delta x. So I'm going to rewrite what I have in green with that little fix that I made, which will now be 1 plus 2k over n. And then that function needs to get multiplied by delta x, so that's 2 over n. F of xk delta x. Oh, I missed a squared, right? Thank you. Yep. Yep. Did I miss it down? Oh, yeah, and I had it written. I had it written in the f of xk. Yep, thank you. I guess that should be green. It was green down at the bottom. Yep. Cool. All right. So try number 5, sine of x over 2 dx. from 0 to pi. It's pi minus 0 over n. So you start with the upper limit and subtract the lower limit. Yep. Yeah. The only time delta x would be negative is if you were, because we read these, I know this is all new. We read from here to here. So we're going from 0 to pi. So as long as we're going to a positive number, we're going up, I should say, not to a positive number. As long as we're increasing, then that will always be positive. I think you need the word sign in there, yeah. Yep.
Right, and that flips up to the numerator. That flips up to the numerator.
Pi over n, 0 plus pi k over n. F of xk is sine of pi k over n over 2. Because it's this function, which is the sine of x over 2. Mm-hmm.
Is that the right like simplification of that? 2 pi k over
No, it would be over 2n. Damn it. All right. So there is that the over 2 kind of throws us, but hopefully everything else kind of worked out. Nk over 2n. Yes. Okay. So our delta x in this situation is delta x doesn't have a k in it though. Delta x is just b minus a over n. Pi over n. Okay. Especially when we start working in the, especially when we start working backwards in the next section, that delta x is just the width of your interval. So if I go from 0 to pi, I've gone pi over n. If I go from -2 to 0 on the other side of my example, the width of that interval is 2. That's why we got 2 over n. So that numerator represents the width of your interval you're integrating over. Because our a equals 0, our xk is easy. Whenever your lower limit is 0, your xk is just one term, and that's pi k over n or pi over nk, however you chose to write it. Both of those are fine. And then that makes our f of xk without any simplification. And again, worst case scenario, just don't simplify it. It's going to be the sine of something over 2. I made that bar excessively wide just to emphasize that my thing needs to get divided by 2. And that thing is the xk. So that's pi k over n. So pi k over n divided by 2. That is the same as pi k over n times a half. That's how the 2 slides into the denominator. Okay. But again, if this were an FRQ, you leave it like that. Don't mess with it. Messing with it only possibly makes it wrong. So that makes our limit, the limit as n goes to infinity of the sum, because it's left, starting at 0 and ending 1 short. If you think back in the tables in E2, that's kind of how those worked too. If you were doing a left limit, you wouldn't use the last one. If you were doing a right limit, you wouldn't use the first number in the table. And it's just f of xk delta x. So that is going to be, I'll clean it up, the sine of xk over 2n. And we're going to multiply that by delta x. I missed it, pi xk over n, right? I missed a pi in my green. Or it's pi k, that's what, yeah, pi k, and xk. Got it, thank you. Yeah. The hard part is copying, not doing the calculus, right? Since there's no sum there, it's just sine of something times pi over k, I didn't have to add an extra set of parentheses in. All right. So that was the straightforward way. Let's do it backwards. This is the fun. All right. So what we want to do is we want to pick things out and kind of reverse engineer all of this. Let's start in the same, what's that? That is going to be, what, 5x minus 1? Yeah, it is going to be 5x minus 1. But let's start with our delta x. What's delta x in this thing? Yeah, 5 over n. That's what we're going to do next. And now let's identify our xk. Yep, 2 plus 5k over n, 5 over nk. That just highlights that you have your delta x times k there. That's the only reason I wrote it differently. So then the function, which is going to be this whole piece right here, 5x minus 1, you got it. So we're taking the 2 plus 5 over nk and we're taking the 2 plus 5 over nk and just replacing that with x. And we end up with 5x minus 1. So back from our xk, we should be able to pull our a out of that. What's our a? 2, yep. So that's telling us that a is 2. Trying to get my... And this is why I said this earlier, the delta x, which I only have written as delta, I'll fix that in a minute, the width of my interval is 5. So if I'm starting at 2 and my width is 5, my b is, got it. Cool. So b equals 7, and that comes from there. All right, so let me fix this up with delta x. I think we're good to write our integral. Or yeah, to write our integral. So we have the integral from 2 to 7 of f of x. I guess I should probably have an xk written there, if it's f of xk there. But this time we're going to write just f of x, so we will write 5x minus 1 here. And then oddly enough, we are perfectly fine to just write dx there at the end and not necessarily worry about that dx being distributed. If this were 5xk minus 1 delta x, then I would need to, I need a parenthesis there. But in the language of integrals, we sort of treat like the integrals like a starting and stopping parenthesis. I'm going to integrate the function up until I see what I'm integrating with respect to. But again, that dx is taking the place of delta x. Cool. All right, letter B. This one has a small typo in it. At the end, it should be 4 over n. That's just me thinking n and k are the same letter when I type this up. So the easy part, delta x is 4 over n. xk. It is. Can we rewrite that in a different order so it matches the way we normally see it? Yep, 4 over nk. Cool. All right. Which makes our A, yep, and our B, yes, because our interval width is that numerator of delta x. So A plus B has to give you the numerator. No, sorry, I'm wrong. A plus the numerator has to give you B. And then that makes our f of xk to e to the x. Yep. So here in this example, we have the integral from -1 to 3 of our function, which I should have written as xk there. But now I'm using f of x, so 2e to the x dx. Every integral needs to end with d something dx. Okay. So letter C, as I was playing around with it this morning, has that same typo with the n and the k. And although it would work just fine as an example, when you plugged k in there, you'd end up taking the ln of 0, which is a problem. So I am not going to have this say ln. I'm going to have this say cosine. This is a quick and dirty hack to deal with the fact that it's trying to get you to do the ln of 0. All right. Okay. So this one's a little bit of a trickier example. One piece of it is, let's start with the delta x. Yep. Can we get the xk the way we want it? A plus delta x times k? The problem would be, though, that the -1 would still be over the n. What's going on here? This is counting from k equal. So the problem would be that, like, if you tried to get this in terms of just a number plus 2k over n, which is what we need, separating it out, you could say 4k over n, which you can easily just turn into a multiplication to get it to say 2k over n. But then your a would be 1 over n, and that's a problem. A can't be 1 over n. But the reason I have this here is just to show you that there are a bunch of different ways to do this. The fact that this starts with k equals 1 and goes to n makes it look like it's a right sum. But what's really going on here is the thing, if I plug 1 into this, I'm starting out with 0. And then the next one, when I plug 1 in, I've got 0. When I plug 2 in, I've got 1. This is literally just I gotta get these right. It's a left sum described as a right sum. Another way to get those exact same results would be to write this as the limit as n goes to infinity. Since I'm saying it's a right sum, since I'm saying it's a left sum disguised as a right, let's write it as a left sum. My goal here is to get, yeah, n minus 1 at the top, thank you. Yep, there's one step ahead of me. When I was starting at 1, these things counted up 0, 1, 2, 3. But since I was starting at 1, I had to write k minus 1. But if I start where I'm supposed to, I actually just end up with 4k over n. I forgot my cosine. I changed it to cosine. Yep. It was just behind the scenes. When I tried to put this in Desmos earlier, it didn't work out because you can't take the ln of 0. Notice that still where k minus 1 was counting up 0, 1, 2, 3, now the k is counting up 0, 1, 2, 3. I don't think I have any examples like this that you guys have to figure out. But if they ever, I mean, I don't know, they throw one at you, they're kind of, it could get confusing, but this is just another way of writing a left sum. You can still index from 1 to n, but then you have to take the 1 away. Instead of taking it away from the indexes, making it 0 and n minus 1, you could take it away in line and write k minus 1 there. So that makes life a lot easier. Because now we're going to look at the right-hand side. X of k needs to be something times delta x, right? So this one's a little bit different. I've got to multiply something by delta x. I've got to multiply it by k. Gotcha. So that is, but that's not what we have there. I know what I need to do. I'm just not thinking it out loud, right? That has to be our delta xk, right? Because if I put anything else there, if I put the 4 there, I'm going to be wrong. So how can I rewrite this in terms of our actual xk? Cosine of what? Yes. There we go. So that means that our f of xk is cosine of 2xk. So you kind of had to pull that 2 out of the 4k over n and make it a coefficient of the xk. So I think we just need to identify our a and our b. What's our a? 0, yeah. There's no plus. It's easy to identify when a is 0, which makes our b not 4, 2. Always go back to delta x for it. So this is the integral from 0 to 2. I actually remembered to write the xk there. And then make sure of cosine 2x dx. So the first, this one had 2 tricks in it. I kind of a little bit overkill here, but the first thing I don't think I'm going to ask you guys to do. So I won't ask you to go from one weird notation to another notation. That's me changing the limit. But you may see this where your delta x and the coefficient in front of the k don't match. When that happens, you do have to make that adjustment. If xk is 2 over nk, but my argument is 4k over n, then I actually have 2 xk's sitting right there. This is 1 xk, this is 2 xk's. All right. Final example. It does turn out that these limits could represent different integrals. The integrals will all have the same value, but they will be different integrals. So I'm going to ask you to do this, or we're going to do, not ask you, but we're going to do it 3 different ways. We're going to assume that the lower limit is 0. Then we're going to assume that the lower limit is 1. And then we're going to do something a little bit weird with the width of our interval. Letter C is not going to be the width that we would use for our other ones. And I'm also going to add the condition that the lower limit is 0 here, just so we don't have to guess. I think, wait, is that the condition I wanted? Yeah, 0. Okay. So now, example A isn't exactly the way that we probably would have done it without these directions. But let's start where we always start. Let's identify our delta x. So we want to write an integral for this. What's our delta x? 3 over n. The problem told us that our a equals 0, which means that our b is how much? 3. Yep. B equals 3. All right. Okay. So that means that our xk which I can still do in blue, is 0 plus delta xk, so 3k over n. So what is, in this instance, what does that make our f of xk? Yes, 1 plus x, the quantity squared. So 1 plus x sub k, the quantity squared. That's enough to write our integral. So this represents the integral from 0 to 3 of 1 plus x but squared dx. All right, let's rehash that, but make the lower limit 1. Our delta x is still 3 over n, but this time our a is 1, which makes our b, nope, 4. Next, our width is still 3, b equals, oh, I can't do my colors. There we go, b equals 4. Now what's our xk? 1 plus 3k over n, right? Because our xk always has to start with a plus. So now what's our f of xk? Easier than that. You went the opposite direction of where you were supposed to go. So pull xk out of what I have underlined in green and just make it x squared, xk squared. Again, only because I have written as f of x. Okay. So the integral on the left is equal to the integral that I'm about to write, which is the integral from 1 to 4 of x squared dx. So two different functions related, two different functions, two different bounds, same result. And now letter C, probably the tricky one. In this case, if the width of my interval is 1, what does that lock delta x into? Over n. Which means that I need to make this summation algebraically equivalent, but not have 3 over n here, but 1 over n here. So I'm going to divide this by 3 and make it a 1 and put a 3 out front. That's algebraically equivalent, right? If I multiply by 3 by some weird green underlined function and then multiply by 1 over n, that is equivalent to just multiplying the green function by 3 over n. So in this case, my a was locked in as 0, and my b is going to be 1, because the width of my interval is 1. My xk is k over n. And now probably the hard part about this example is, what's my f of xk? Quantity squared, yeah. If you put k over n in where I have xk, you have this. Agreed? Yeah, because then this 3, the 3 coefficient pops out. So a third integral that is equivalent to the other two, integral from 0 to 1 of 3 quantity 1 plus 3x but squared dx. I don't think this is the thing that you would have to do more often than not. I see this as one of those sort of questions where it's like, hey, here's a limit. Hey, here's some integrals. Roman numeral 1, Roman numeral 2, Roman numeral 3. Which of the following integrals are equal to this limit? And that answer is all three, right? So that's where that comes up from. Like there's no other reason to arbitrarily make the width 1, which kind of messes everything up. Like you then have this weird 3 out front. You end up with the coefficient in front of your x. This is the most complicated integral going. So this last letter C isn't something that I expect you to have to do on the reg. It's not good in the grand scheme of things. Maybe there's 1, possibly 2 multiple choice questions on this. All right. That was a long one, right? Fun stuff. I know. Absolutely, because you're calculus students. Yeah, I don't know what I was. Yeah, that was wild that I'm like, oh, I think I looked at the assignment and not the, but even that's just the way my brain, I always think I can do more than, I'll never learn that lesson that I can't do more than. So tomorrow we will give you some time to practice on this since it's the short day. We'll start E4 on Thursday, which will probably be a virtual day. I will give you E4. I will have E4s here for you tomorrow. Yes, like that. No, like that's still All right.